everyone, welcome to this design practice module 13. Today we would like to just investigate what are the changes which have been brought in because of this new concurrent engineering approach. In the last few modules we have been talking about if the whole cross functional team works together with inputs from quality, inputs from marketing and sales, or even service, or inputs from manufacturing, the design gets altered suitably to the most economical, most optimized design. But let us look at in the serial engineering approach, when we started, we defined certain paradigm based on which there was a unit cost which was reported or a setup time which was reported, how it gets changed subsequently because of the concurrent engineering philosophy. So, our problem example here was again about evaluating three different options. We had three different manufacturing options in mind. One was a turret lathe option, another was an engine lathe, okay, and the third was the automatic screw cutting machine. And these options were laid out in terms of unit processing cost, in terms of setup times, in terms of unit processing time and process standard deviation. And we found out that these three options would have different unit costs as reported in the manufacturing handbook, okay, and this was a data given by the manufacturing team also. Different setup times, which was like 20 minutes for option 1, 25 minutes for option 2 and 50 minutes for option 3 respectively. So, the unit processing time, that is processing time per unit in this particular case for the turret lathe was reported to be about 1 minute per unit, 0.8 minutes for the engine lathe in the component and 0.70 minutes in the ASM, the automatic screw cutting machine. Similarly, the process standard deviation which was recorded for these three different options, manufacturing options, was 0.003 in the first case, 0.002 in the second case, 0.001. The minimum standard deviation or most accurate system was defined to be the ASM. So, having said that, let us now sort of compare both the serial and the concurrent engineering approaches. So, in the serial engineering approach, if you may recall, we had obtained all these values related to number of rejects for all the three different machinery. Then we also obtained data related to the unit cost, okay, probably time of manufacture as well. So, these were recorded for all these pieces which were supposed to be produced, namely about 1000 pieces which were supposed to be produced, and we found out that with a mean of 1 inch diameter and a process standard deviation of 0.003 inches that is given for the turret lathe. In the turret lathe, the unit cost of the product which came out happened to be about 23.97 currency units, in this case US dollars, okay, for the turret lathe alone, okay. And the setup time which was provided in this particular case was about 20 time units. So, let us say this is in minutes, the time unit is in minutes. So, the setup time was exactly 20 minutes for the turret lathe, and the number of rejects, which was a measure of the quality in this particular case, number of rejects happened to be about 465 units. These were the numbers produced which were defective. So, for every 1000 pieces of production in the transformation system, you have to enter exactly 1465 pieces, out of which 1000 will emerge out and 1000 good pieces will emerge out, and 460 would be the scrap percentage which would get produced, okay. So, the inputs were again 1465, outputs 1000, scrap units 465. So, number of rejects in this case was 465 units for the turret lathe. So, let us say we are evaluating alternative 1, okay, for the serial engineering approach, And now we would like to also calculate the manufacturing lead time here. So, let us just do that. So, manufacturing lead time for the serial engineering approach happen to be again the total amount of setup time that is being utilized plus the number of units turned on turret lathe I will say first option, okay. Turret lathe is the first option times the time per unit on the turret lathe. So, this then happens to be about 20 plus 1465 times 1.00 time units, which is about 1485 time units or minutes in this particular case. So, the serial engineering approach produces with the turret lathe a product which has a unit price of about $23.97, rejects about 465 units and takes a manufacturing lead time of 1485 units, and this is the alternative which was chosen in the serial engineering approach. But if you look at the concurrent engineering philosophy, we consider a scenario in meeting 3, let us say, that reflects the concurrent engineering approach. So, if we suppose that it takes about 0.70 units of time or minutes to process in the ASM or the automatic screw cutting machine, we will have subsequently at 0 reject level the number of good options which are there 1000 pieces to be produced in a very, very short amount of time. So, let us see that. So, when we talk about a concurrent engineering approach, as you may recall, so in this particular case we considered a scenario as in meeting 3, which talks about that the rejects are higher and something has to be done for the customer to accept the overall quality level. And so, the team explores the possibility of using a more accurate machine, that is ASM machine, to process. At a much more accurate level. Okay. So, here in this case, as you may recall, the unit cost which came out was about close to again $22, and a setup time, particularly if you consider the ASM, comes to about 50 time units or 50 minutes. Okay. And similarly, if I look at the number of rejects in this particular case, the number of rejects were 0, that is how it turned up, and the manufacturing lead time which happens is constituted of a setup time again plus the machining time, which is the number of units on ASM times time per unit that it takes on an ASM. So, this happens to be then about 50 plus 1000. Obviously, in this particular transformation in the ASM machine, as emerged in the third meeting, if the transformation changes from a turret to an ASM, in this case you have exactly 1000 pieces input, 1000 pieces output with almost 0 scrap coming out. Okay. So, that is how accurate or that is how precise this particular machine is. Okay. So, in this particular scenario, as we know, the number of the manufacturing lead times came out to be about close to 750 minutes. Okay. So, if I look at from a serial engineering to a concurrent engineering approach, this whole fact of reiterating and somehow using feedback from different sources and trying to imbibe in the whole process of thinking the importance of some areas which were not considered to be as important in the serial engineering, areas like quality for example, it helps us to resolve the scenario and helps us to get into a situation where we are operating, as you see, at a much lower setup time. okay, the manufacturing lead time. So, earlier it was 1485 minutes and now it is about 750. So, about half, okay, and that also at a price which is more or less similar. It's the price is not changing much. You see, $23.97 per piece was the price which one could get on the turret lathe, and about $22 is the unit cost which could be gotten on the automatic screw machine. So, in fact, it is for the better that the cost also is going down by maybe $1 or so, and you are able to get at a much lower manufacturing lead time, at a much lower cost, a scenario where the number of rejects are 0 or number of the quality is very high. So, this happened because of the involvement of several people at the very outset, and the design which is going to be a better design obviously is going to include the same specifications 1 plus minus 0.0003 on the ASM. Whereas, at the outset if you look at ASM and if you look that the process is expensive, you find out that it is not going to work. Okay. So, it is about a trade off again. In this case, as you saw, the trade off was between the number of rejects. If the number of rejects are lowered, still the cost comes down, and the processing time is lowered, still the cost comes down. The question is, what is going to be the decision of a company, and this decision could have never arisen had you not involved quality from phase 1. Okay. So, that is what the benefit can be envisioned as when we talk about concurrent engineering approaches. So, with this, I think one thing is very clear. If we looked at what are the improvement levels, you would like to sort of see percentage wise what are going to be the different improvements in the different parameters. So, let us say improvements in unit cost of the product, the quality levels for the manufacture of the product, and manufacturing lead time for this product. So, you see that the percentage improvement in unit cost is again about 23.97 minus 22 by 23.97 as about 8.21%. So, there is a reduction on the unit cost by 8%. Improvement in quality is humongous. So, the improvement in quality is almost, I would say, 465 defectives to 0 defective. Okay. So, this is more or less a total quality managed system with very less scrap. So, 0 scrap in comparison to a scrap generated earlier, and then of course, the percentage improvement in manufacturing lead time is also tremendous. It is 1485 minus 750 as a percentage, represented as a percentage is about 49.50%. So, you can think of the improvements in the cost and the lead times, okay, and also the quality, okay, just because you involved everybody in the decision making process from the very beginning. So, there are various other advantages also that concurrent engineering has to offer. One of the most important benefits of concurrent engineering is, although not explicitly addressed in the very simple example that we did in the last few modules, in many large development projects, particularly when we are talking about product development, the major issue which happens is the lack of communication between the different members, and that lack of communication can be resolved at the very outset when we talk about a concurrent engineering philosophy or a concurrent engineering approach. So, you can probably lead yourself to extensive amount of engineering on the various phases of the product life cycle when you are putting a concurrent team or concurrent engineering team in place, cross functional team in place, because everybody will bring his own perspective on the table related to not only just the design and the manufacturing phases of a product, but then related to the sales and after sales part, and also to some extent even people who are going to look after how the product is. So, up to the disposal phase of a product life cycle. So, all the associated experience is coupled at the very beginning in the design process, okay, because of which maybe delays can be avoided. For example, that let us say we just categorize it this way, that in serial engineering approach, the shortcomings, if we look at, are first of all lack of communication during designing. Of a product, okay, or lack of communication between all stakeholders. So, who are the stakeholders? So, stakeholders are members of various part of the product life cycle. Okay. Stakeholders can be the design team, they can also be the manufacturing team, they can be the sales and marketing team, they can also be somewhere around here quality team, they can be team related to let us say the service of the product and even the disposal. Okay. So, these are the different aspects of the life cycle of a product before from the designing to the realization to the sales. And what you are essentially having in a serial engineering approach is a lack of communication between all these different teams, which get resolved when we talk about concurrent engineering. So, the lack of communication gets addressed, and so therefore, concurrent engineering may result in, I would say, better engineered products because of this knowledge that gets packed on to the product from the very beginning. Okay. So, may result in better engineered products, or you can also record this as optimized solutions. So, we are not only concerned with the product, but also the solutions with respect to the production as well as how it channels through to the consumer. So, typically if you had this shortcoming, if you had the lack of communication in serial engineering, this leads to product delays, because at every phase when the product passes through, there is some engineering change or the other which has to be introduced every time to the design phase. And so, definitely this is not a very good approach in the serial engineering strategy that some companies may envision. So, the increase in time to reach market can influence various aspects of a product. It can lead to probably influencing the acceptance, the overall acceptance of the product, the market position related to the product, the project cost, overall quality levels, all those things are affected very much when we are talking about the serial engineering philosophy. So, these can be addressed quite well, and it should be on a firm basis that one should be ready to adopt the concurrent engineering strategy. So, we will now talk a little more details about how do we characterize a concurrent engineering environment, what are the different components which are needed for looking into such an environment, and we will actually endorse this through a case study which would talk about the computer aided acquisition and logistic support, which was hired by the electronic systems working group by the CalC corporation, which led to a very structured organizational nature, and which led to this communication increase by several folds, leading to overall benefits as associated with the different products which were launched through such a platform. So, we will talk about this electronic systems working group report by Linton and co-workers. Okay, it is a case study, and in context of that we will try to understand what is going to be the concurrent engineering environment, how do you implement such an environment for any kind of product complexity, product technology, defining program structures, program futures, competition in the market, and many other parametrics like business relationships, team scopes, resource tightness, schedule tightness, so on and so forth. So, we will start working on this problem probably from the next module, and I would like to close this particular module, but in the next module we will just discuss this case study by Linton in a more appropriate manner. Thank you very much.